Welcome to our discussion on inverse trig functions. Let's start with the inverse sine function. Now, the sine function is not one-to-one. If we graphed the sine function normally, it would fail the horizontal line test miserably. So what we have to do is restrict it to a piece, a section, that doesn't curl back on itself. And since we like to include the origin, we can't really start from the origin and go out one full cycle, because as you move out it doubles back on itself, right? So if you go from the origin in both directions, you can get a bigger function, and we end up having this interval from minus pi over 2 to pi over 2, and that gives us a one-to-one function. Now that we have a one-to-one function, we can find its inverse, right? Don't worry so much about trying to graph it. Just think about what the inverse function means, and it means what every other inverse function means. It brings you back to where you started, right? You got some x's here, and you got some y's over here. Sine takes you in that direction. Inverse sine just brings you back to where you started. Okay? If you look at our picture, this is our domain, our range, right, is from minus 1 to 1. So when we flip it and do the inverse, we're now going to have a domain of minus 1 to 1 and a range of the minus pi over 2. Right? So domain is from minus 1 to 1, and this is our range, which is nice because now we know we can only plug numbers into sine, inverse sine. We can only plug numbers into the inverse of sine that are between minus 1 and 1. Here are some examples. Is square root of 3 over 2 in between minus 1 and 1? Well, yes, because square root of 4 would be 2. That would give us 1. So this is a little bit smaller than 1. Negative 1/2, that's good. But what about sine inverse of 3? Right? Inverse sine of 3 is no good. But the other ones we can work on. Inverse sine of 3/2 just means what value would I have to plug into sine to get 3/2? And that's where you want to go back to your first quadrant of your reference angle and remind yourself, right, you've got 30, 45, 60, and you have these heights. You know 45 is square root of 2 over 2. It's the 30 and the 60 that give you square root of 3 over 2 and 1/2. You just can't remember which one is which. Well, which one of these two is taller? This one's taller, right? Which one's bigger? Square root of 3 over 2 or 1/2? Square root of 3 over 2. So this is the dot that gives you 1/2 comma square root of 3 over 2. And this is the dot that gives you square root of 3 over 2 comma 1/2, right? This is where x, your cosine value, is square root of 3 over 2, and your y, your sine value, is 1/2. And this is the opposite. This is 60. So we need to do sine of 60 gives us square root of 3 over 2, and sine of 60 is pi over 3. Is pi over 3 in our interval? It is, so that's the answer, pi over 3. Okay, the next example, they want to know when does sine give you negative 1/2. Well, if we go back to our picture, we know that sine equals positive 1/2 here at 30 degrees. So wouldn't it be negative down here at negative 30 degrees, or negative pi over 6? And lo and behold, negative pi over 6. Since 3 is not in the domain, we can't even do it. How about the inverse cosine? Well, very similar process. Again, we like to include the origin, but because of the way cosine works, we can actually just do one side, right? So we can go from 0 and above go from 0 to pi. So this function we're going to restrict to 0 to pi, which gives us a 1-to-1 function. And on that interval, our range is 1 to -1. Again, don't worry about the pictures, who cares? What's more important is this. If we're looking at our inverse function, we now have a domain of -1 to 1 and a range of 0 to pi, right? So our domain -1 to 1, our range 0 to pi. Here's some examples. Square root of 2 over 2, -1/2. Well, we just talked about it, right? Thinking about our first quadrant, we know square root of 2 over 2 happens at 45 degrees, or pi over 4. So we check and go, yep, pi over 4 is in that interval from 0 to pi, so the answer is pi over 4. -1/2, normally you'd think -1/2 happens when you go around over to this side, right, and get -1/2 for your cosine distance. But if we're over here, is that going to work? We always got to check our interval. Cosine equals -1/2, right? Cosine of what equals -1/2? Well, cosine of 2 pi over 3, 2/3 pi, gives us -1/2. And since that's in our interval, we're good to go. Right? And our reference angle, our reference quadrant, cosine is 1/2 right here, and square root of 3 over 2 here. So that's 60 degrees, which is pi over 3. So we know that we have to be over here, where we're 60 degrees above the x-axis, which is another, pi over 3. Or if you go all the way around in this direction, that's your 2 pi over 3. And 2 pi over 3 is in that interval of 0 to pi, so we're good to go. Inverse tangent. Well, tangent's 1 to 1, so we don't have to restrict it. We can just take one whole piece of it. It's minus pi over 2 to pi over 2, that interval, and then those are your vertical asymptotes. On that interval, we get, it goes up to infinity, down to negative infinity. So when we're looking at the inverse function in red, you can see that its domain is everything, and its range now is the minus pi over 2 to pi over 2. So this is the first of our inverse functions that we have an entire domain. The other ones all had restricted domains. Some examples. Finding tangent inverse of 0 just means asking the question, when do we get tangent of 0? Tangent, remember, is sine over cosine. And if that equals 0, that means sine has to equal 0. And when does sine equal 0? But right here, right? Sine is our vertical height. So that's going to equal 0 at 0. And that, of course, is in the interval for tangent, right? We're asking what value would we plug into tangent to get 0. We would have to plug in 0, and that's in the domain of our tangent function. So that's our answer. If we're trying to get negative square root of 3, when is tangent equal to negative square root of 3? Well, in the first quadrant, here at pi over 6, we have square root of 3 over 2 and 1/2. And then up here, we have 1/2 square root of 3 over 2. Remember, we want sine over cosine, sine over cosine. So if we did this one, we'd have 1 over square root of 3. Nope, we want square root of 3 over 1. So the reference angle we're looking for is pi over 3. But that would give us a positive square root of 3, right? Square root of 3 over 1, positive. We want negative, which means we just have to go negative the same angle, negative pi over 3, which is in our domain for tangent. It's defined there, so that ends up being our answer. How about evaluating inverse trig functions using a calculator? Well, they seem to make it look a lot more difficult than it really is with all this stuff about where your x's are defined and where your y's are defined. Just draw a picture, look at the picture, and make sure everything is okay. Define inverse cosecant of 2. You're trying to find what value of cosecant equals 2. And that's how you solve backwards, right? We're not actually using a calculator here. We're just going, all right, cosecant. What is cosecant? Cosecant is 1 over sine. So if cosecant equals 2, what does sine have to equal? 1/2, right? Because they're inverses of each other. Sorry, not inverses, they're reciprocals of each other. So 1 over it. So when we're asking for inverse cosecant of 2, we're asking cosecant, pretend like you don't know what this is, cosecant of what equals 2, which is really asking sine of what equals 1/2. And again, you'll see why it's so important to really get to know this first quadrant. This is when your height is 1/2. That's your first one. That's 30 degrees. So that's pi over 6. And that's why the answer is pi over 6. Okay, so it all comes back to drawing the picture. Just draw the picture. Now, if we want to use a calculator to evaluate these things, we have to know these ideas, because it comes back to this. If I'm trying to find something that makes cosecant a number, I'm really looking for 1 over it for sine. So that's where this is coming from, the idea that to find inverse cosecant of x, you can do inverse sine of 1 over x. And same thing for secant and cotangent. Cotangent's weird though, you have to do a shift. Here's some examples. To find inverse sine of 0.75, you just got to make sure you're in radian mode. Type it in, you're good to go. Do cotangent, you got to do inverse tangent of 1 over it. Do cotangent of the negative 1, however, you got to do pi plus inverse tangent of 1 over it. So that's all you got to remember for that, is that if you're going to do an inverse tangent of a negative number, you got to add pi to the inverse tangent of the reciprocal. Some more examples. To find tangent of 0.99, inverse tangent of 0.99. I believe this is a typo. You can just plug it straight in to inverse tangent. To find inverse secant of 25, you're finding inverse cosine of 1 over 25, and then inverse cotangent of negative 1.3 again is pi plus tangent of it, only in this case we're in degrees instead of radians, so you got to make sure that first thing you reset your calculator degree mode, and then instead of adding pi you're adding 180. Okay, so same thing, it's just whether you're in degree or radians. Last but not least, we can find some exact values of composite functions, just like we did with other composite inverse functions. If we're taking inverse sine of something, we should just get that something back as long as everything is defined properly, because remember, these functions aren't defined on all domains, so it's not always just going to be whatever the something is. Now with sine of negative pi over 2, negative pi over 8, because that is in the interval of where we restricted sine in order to make it 1 by 1. In order to make it a one-to-one function, we had to restrict sine to this domain, negative pi over 2 to pi over 2. If you don't remember, it's back on the earlier slides. Because what we're looking for is in that restricted area, we're fine, because we can take the sine of it, get an answer, and then the inverse sine gets us right back to that number. For the cosine example, 5 pi over 4 is not in the interval where we defined cosine, right? We restricted cosine to 0 to pi in order for its inverse to work. 5 pi over 4, that's bigger than pi. That doesn't work. So you have to treat cosine of 5 pi over 4 as 2 pi minus 5 pi over 4. You're basically looking for the equivalent answer in the other quadrant, right? If we're at 5 pi over 4, 5/4 pi, we're all the way down here, right? Because this is pi. So if we do 2 pi minus 5 pi over 4, we're going to get the same angle, but it's going to be in the quadrants we need it to be. And that ends up being 3/4 pi, right? This is pi plus a fourth. Really, that's your reference angle right there of 1/4 pi. But since we're dealing with cosine, we need it over here on the left because we need to keep it negative. So if this is 1/4 pi here, what's left over is the 3/4 pi. I wouldn't worry so much about, well, why is it 2 pi minus that? Just draw the picture, find your reference angle, put it back to an angle that works for our function. For cosine, we've got to be from 0 to pi. For sine, you would draw your picture like this, right, and know that you'd have to be from pi over 2 to negative pi over 2. And if it goes outside, you just have to figure what it is and flip it and find the right one that's in this interval that fits. Another example, this is where it gets a little trickier because we're no longer doing cosine of inverse cosine or sine of inverse sine or tangent of inverse tangent. We're now mixing and matching. We're now doing cosine of an inverse tangent or sine of an inverse cosine. So we have to go back to our SOHCAHTOA and remember what each of these functions really gives us in terms of the angle in the line. So for the first example, and we'll write it back up here just so we know what we're doing. We're trying to find cosine of tangent inverse of 2/3, right? Well, tangent inverse of 2/3 is basically saying what angle do you have to put into tangent to get an answer of 2/3. And we know that if this is my angle, right, this is my theta, tangent gives me opposite over adjacent, right? It gives me this length over this length, opposite over adjacent. SOHCAHTOA, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, that's an A, and tangent is opposite over adjacent, SOHCAHTOA. So tangent is y over x. And since that equals 2/3, that just means y equals 2, x equals 3. We can plug it into our Pythagorean theorem, right? This is r squared equals x squared plus y squared, and we just solve for r. We get a radius of 13 for r, so that means to get this point, our radius for our circle has to be square root of 13. Now we're going to do cosine of that same angle. Well, cosine of that same angle, remember cosine adjacent over hypotenuse, gives us x over r. So cosine is x over r. X we already know is 3. R we just found is square root of 13. 3 over square root of 13, and then of course we rationalize the denominator, and there's the answer. Okay, once again, we can do this one the same way. Draw a picture. Now you don't have to make your picture accurate as far as knowing that this has to be the right angle. Why can't we do this? I know that if I have an angle, call it theta, here's my point, right? This is x, this is y, this is r. Cosine of this angle equals x over r. X over r equals -1 over 4. So x equals -1, r equals 4. Got all that from my picture, didn't need this picture over here. R squared equals x squared plus y squared, right? Plug in everything you know, plug in the r, plug in the x, solve for y. Y equals the square root of 15. Still, got all that from my picture. Don't need this picture over here. Still use the same picture we had from the previous one. Now, we're doing sine of this same angle. Sine of this angle is y over r, right? Opposite over hypotenuse, right? Radius, hypotenuse. So y over r is square root of 15 over 4, and there's our answer. We don't need to be accurate. Yes, because it's a negative x, so we're over here, but who really cares, right? Draw a picture, know your relationships. Cosine is adjacent over hypotenuse. Sine is opposite over hypotenuse. Tangent is opposite over adjacent. And that's it. Just draw this picture, figure out what has to equal what, fill in the bits and pieces, solve for the missing third piece, and then evaluate it. It's that simple. Don't let them confuse you with extra pictures. It always comes back to just one simple picture. Okay, one last example, a word problem. We've got a camera that's 20 feet from a counter. The counter's 30 feet wide. We want to program our security camera to oscillate back and forth, right? Sweep back and forth to cover the entire counter. So we need to figure out what angle does it need to bend in both directions to cover all 30 feet. Well, there's our picture, right? That's just like what we had before. My angle, and I can draw it over here. Here's my angle. They're calling the whole thing theta, so they call this theta over 2. But, I would just call it theta. And then I know my answer is going to be twice that. So I'll call this theta as well. This is my y, this is my x, this is my r. Well, I know in this case, right, from this picture, since this is where the camera is, and it's going to be doing two of these, can we see now that this is x and this is y? Right? Tangent of this angle has to be y over x. So tangent of theta has to equal y over x, which has to equal 15 over 20. Right? So if we want to solve for theta, we now have tangent of some angle equals, what is that, 3/4 if we reduce. Well, to solve for theta, we have to undo tangent. How do we undo tangent? Do tangent inverse of both sides, right? Tangent inverse, theta equals tangent inverse 3/4. Plug tangent inverse of 3/4 into your calculator, and blammo, you get 36.87. And remember, that was just this piece. The other piece is the same, so you double it, and there's the angle. You need to set your camera to basically go through a 74-degree angle, and it'll cover the whole counter. That's it, guys.